all movement stops.
Isn't it impossible to get to absolute zero?
It has been so far. Yeah, one of the, is that the thermodynamics? One of the laws of thermodynamics says you'll never actually get it.
We got pretty
darn
close in the
close.
lab though.
Pardon?
We've gotten pretty close in the lab though, like 0.007, I think.
Wow.
Yeah. I think, yeah. And in deep space, they can get to like 0.01, I wanna say.
They have gotten closer than that. They've gotten into picokelvin before by, there are certain groups that are just trying to break the record. All right, so my temperature of sound, or sorry, the speed of sound should be 331 meters per second times the square root of 295.25 divided by 273.15. Which gets you something which someone will share with me, or us. Which should get us close to what John was saying earlier.
$344.129
Units?
meters per second. Yeah, meters a second.
I hope so. One, I got meters per second right here. What's inside the radical is unitless. I have meters per second here, and also I'm finding speed, so.
Yeah, I don't know, I'm thinking Kelvin.
Yeah, I got fast and loose with the units that were inside here. In the end, what's inside ends up being unitless.
Oh, I got something better. Oh, did you drop the 0.3? The 331.3?
Oh, I dropped the 0.3 just then.
I got a 344.442.
Okay, all right. So now that we know what the speed of sound is, we can calculate what the frequency is for the first harmonic. And get some room here. And a different color, just for that. The typical stunning visual effect. So using this formula here, we have 344.442 is equal to, and that is a sad marker, less sad. I need to figure out what the wavelength is. Well, I know it's 2 times the length of this tube, and so let's figure out what the length of the tube is. And it's just simple, let's just measure it.
89 centimeters.
Anybody want to place a bet with him?
Okay, here,
Of course, now you have an
76.
advantage because I actually have it up here.
I'll stick
78 centimeters?
75.
83.9.
You're pretty close, Nick.
So my length, 83.9 centimeters, but we want it meters so that we don't have to worry about units later, like 839 meters. So this is equal to the frequency times 0.8, oh, twice that.
So it's 167.8 centimeters.
Okay. So times 1.678, technically it's meters, that's meters per second. So my frequency is going to be my speed divided by the wavelength. We're gonna get 200 something.
$205.269.
200.269
No, 205.269.
units?
Um, Seconds? Hertz.
Hertz. The seconds would be in the denominator, it's per second,
Okay.
which is basically hertz. All right, so let me play you 205.269. So it sounds a lot like the last thing I played for you. 205.269.
What program is that?
Online tone generator. They do not sound the same.
No, it sounds more high pitched.
Yep. The reason for that, the reason we can get any sound out of this at all is I'm swinging the tube here. This end, obvious, I hope is obvious, is moving faster than this end. Because this end is moving faster, there's a drop in pressure up here, so there's less pressure on this end than there is at this end. Because there's less pressure up here, air's coming up through the tube. Now, the ribs vibrate the air, which get it actually oscillating so we can actually hear something. Without it, we would hear a swish, but of different frequencies. But in order to get the first harmonic, I have to move slower. The first harmonic might be something like that, but there's not enough pressure difference to get enough air running through it in order for us to hear it. We actually hear the second harmonic. It's not the first harmonic. So let's do the second harmonic and see how close we get. I got the length, I figured that part out. So my frequency now is my speed, 344.442 meters per second, divided by the wavelength, which is 0.839 meters.
It's 410.539 hertz.
So 410.539.
That's closer.
Sounds exactly what we just played. Perfect.
Have you ever tried to harmonize with it?
Let's see how well it does going together. All right, so roughly it's the right sound, but
Pretty close.
how do we actually tell if we are dead on or not? I mean,
Playing both at the same time.
and keep going. That's exactly right so far.
And use a thing to measure or something.
We do have microphones, so we could actually try to run the frequency that way. Yeah, we got time. I haven't done this, I don't think I've done this with you yet.
No.
All right, we have talked about constructive and destructive interference.
Yeah.
So what I did is I took two frequencies and I just plotted them out. They both have an amplitude of 1, just different frequencies, and so these are slightly off. And if you can't look at them and go, oh, they're clearly different, they both start at the same place here, but this one ends on the way down, and this one ends after it's already bottomed out and it's coming back up. So they're slightly different. I then took the blue one, and I traced it onto this transparent sleeve. Let's see if I can get those lined up. So that's the blue one that I've traced onto the sleeve. And now I'm going to put the purple one next to it, getting them to start at the same spot. So the purple one, which is underneath the dark lines here, I have them starting at the same spot, but over time you notice they start to differentiate. That at this point they're particularly much in sync, but they get farther and farther off. Now right now, at this point, it's definitely constructive interference. At some point, well, let's see what happens. So So I basically then added those two together, and I got this graph. So now my amplitude is 2 right here. Will be just shy of 2 actually. And notice that the amplitude is getting smaller as we go. If I extended it out, I get this. So we have this point where there's constructive interference, and then a point where it's completely destructive interference. So if I play this, right, so here's 440 hertz. This is 439 hertz. Could you hear the difference? One was 440, one was 439. Could you hear the difference?
No.
Try one more time.
Some people can, so I cannot. This is 440. This is 439.
No, I can't tell the difference.
I feel like if you didn't tell me, I wouldn't. No.
Yeah, all right, so let me play them at the same time, which was Nick's suggestion. Here's 439 first, and 440. Yep.
That's weird.
That difference there, basically you're hearing it when it's loudest, and then when it gets quiet, then it gets loud again and quiet, and you get that wah-wah sound. That's known as a beat, B-E-A-T. Get ready for the complicated math. Here's the beat frequency. This is how you calculate the beat frequency. I played 440 and 439. Beat frequency, take the difference. So that's 1 hertz.
That's tough, that's hard.
I know. I can go over it again later, but we don't have time to do it right now. Just let it mull over, let it wash over you. The period then, how often it should go quiet is the reciprocal of that, which is
1 second.
1 second. If I played 439 and 440, so 440 or 40 and 439.5, my beat frequency is 0.5 hertz. My period would be 2 seconds. Let's see how well that works out. Okay, let's see, 440, and I need to stop this one. All right, so 439.5 and 440 at the same time. 1001, 1002, 1001, 1002.
And the further you get away, the shorter your period's gonna get.
Yep. And so what we'll do next time is we'll swing this, we'll play that at the same time and see if we can actually hear any beats. There should just be a slight trill because, you know, it's a physics demonstration. Don't expect it to work out that well. We used valve that up when we did the pendulum trying to predict the period. So anyway, I hope you have a wonderful day. See you tomorrow.
Unless we all get sucked up by a tornado.
True, avoid tornadoes.
I'm driving right through it.
If you're gonna get sucked up by a tornado, wait till after the semester is over.
I'll try my best.